let's talk through quantum numbers. We're going to start with n, the principal quantum number, and it really characterizes the energy of an electron at any given particular level that it's at. Remember, these are going to be levels that are quantized as distance away from the nucleus. So we have a nucleus, and then at the n equals 1 energy level, so quantum number n, it would be equal to 1. It'll be a certain distance from the nucleus and at an energy level relative to it. So this n number, it's always an integer, 1, 2, 3, or 4, and it can't be 0. Are always going to characterize the size and the distance from the nucleus or energy level of the orbital or the electron in an orbital. And so the larger the value of n, the more energy that it has, the orbital has, and the less stable it is. And that's because it's further away from the nucleus and it's operating at a higher energy level. Also, we see that as n gets larger, the difference between our energy levels, like between energy level 10 and 11, will be much smaller than the difference between energy level n equals 1 versus n equals 2. And our energy levels are always going to be equal to this negative 2.18 times 10 to the negative 18th times the inverse of the quantum number squared. And so that energy level here is going to be, for n equals 1, is just negative 2.18 times 10 to the negative 18th joules. And then as you go up, that number, that energy is going to get larger. So you see that the negative number here, negative 5.45 times 10 to the negative 19th, it's a smaller negative number. And so it's getting larger as you go up and away from the nucleus. Our next quantum number is L, and it represents angular momentum. So the angular momentum quantum number really determines the shape of the orbital. And the electron's orbital is the area that it is probable of finding the electron. So it describes the areas you might find it and the areas you won't find it, and the areas that are very unlikely to find it. And so angular momentum gives us this shape of the space the electron can be in. The values that it can be are integers as well, just like n, but it can be 0. So 0, 1, 2, 3, 4, 5, all the way up to n minus 1. So you'll never have n and L be the same number. L will always be 1 less than n. So each value of L is also going to correspond to a particular letter that we designate shape of that space the electron can be in, or orbital. And so if you have L equals 0, you have what we call an S designation, and this is the S orbital. For L equals 1, this corresponds to a P shape for an orbital, and we call them P orbitals. If L is 2, then we have a letter designation of D, and we say that the electron is in the D orbital. And then if you have L equals 3, then you have an F designation, or you have an electron in the F orbital. And this can continue on. 4 would correspond to G, and so on. And see, what's changing here is the shape, right? And so that's what's really different about each of these. And so that S orbital is just a sphere, a perfect sphere, whereas an L orbital looks more like a figure 8 of spheres. And the real difference here is that between the S and the P orbital there is a space right here where it's a node. It's where the electron cannot exist. Remember, Schrödinger's wave equation is wave functions. And so we're talking about a mathematical way of representing a wave. And so it will have nodes. And so we go from L equals 0 to L equals 1, and we create a node that takes place as we have this different shape. And then we have 2 nodes for L equals 2, and we've got 3. It's kind of hard to draw this one for L equals F, or L equals 3. And these are planar nodes where there's this little plane of space that the electron can't exist in. All right, our next quantum number is M sub L, or the magnetic quantum number. And the magnetic quantum number is an integer that is going to specify the orientation of the orbital in an XYZ plane. And so that means that these are going to include integer values, and they can be negative or positive, and they go from negative L all the way up to positive L. So if L equals 2, then M sub L can be -2 or -1 or 0 or +1 or +2. And those are all possibilities where an electron can be occupying a space. So that means that there's always 2L plus 1 different values for M sub L, because that plus 1's coming from the addition of a 0 integer into our calculation of the number of possible magnetic quantum numbers that correspond to every single type of orbital shape characterized by a quantum number of L. So let's just kind of walk through some possibilities. So what are the possible values that we could have for quantum numbers if our n quantum number equals 3? So if we're at n equals 3, that really means we're at that third energy level from the nucleus. So if we know we're in that energy level, n equals 3, then L can equal 0, 1, or 2, because 3 minus 1 equals 2. So that is the largest L value we can have. So M sub L can be a number of numbers that are plus or minus L. So it'll be -2 or -1 or 0 or +1 or +2. So the number of spaces, or the number of places an electron can be in that third energy level are, for every L equals 0, we would have, or sorry, L equals 2, we would have 5 possible places. But so here, let me actually write this. So if L equals 2, but if L equals 1, then we could have an M sub L in the -1, 0, or +1, or 3 different places. And if L equals 0, we can have M sub L equal 0. And so this L equals 2, remember, these are going to be our d orbitals. And there's 5 different orbitals that it could occupy within that. If L equals 1, these are our p orbitals, and there's 3 of them. And for our L equals 0, that's our s orbital. Remember that s orbital is just a sphere, and so it has the same orientation no matter how you look at it in an x, y, z plane. But the p orbital, which looks like kind of a figure 8, can be oriented in a 3 different ways. Specifically, if you're in an XYZ plane, you can have it along that y-axis or the z-axis, or you could have it along the y-axis, like whichever axis I didn't say yet of the 3. And for our d orbitals, there's 5 different arrangements that you can have in the XYZ plane. So here's a way of representing all those possibilities we just discussed. If we have n equals 1, we can have L equals 1 and an M sub L L equals 0 and an M sub L equal to 0. If n equals 2, then we can have the L equals 0 and L equals 1 possibilities, so S and P orbitals. We could also have then this, I like to think of it as this entire kind of component is available. And as we increase another level, we kind of lay another number or another layer of different possible orbitals an electron can occupy. And so if we add n equals 3, we then have L equals 0, L equals 1, L equals 2. And within that, we have increasing numbers of M sub L values as well. And this really builds up what a orbital diagram is going to look like. And so these quantum numbers are really kind of giving us an address for an electron. It's telling us where we can expect to find it in an atom. And more than anything else, this is a bookkeeping method for us as we try to wrap our brains around the electronic structure of the atom. And it allows us to keep track of the electrons and keep track of which ones are going to be further away from the nucleus and therefore more likely to be involved in chemical reactions with that atom. So that's 3 of them, and those 3 come out of the Schrödinger wave equation. And then we have another type of quantum value, a 4th number, quantum number, and it is m sub s, and it is our spin quantum number. So this arises out of the behavior of an electron in a magnetic field. And so electrons generally act like a top. So they have a spinning charge, like a magnet. And it means that there's 2 different directions the electron can spin. It can go sort of like clockwise or counterclockwise in a north versus south. And so these if you had 2 that were near each other, one would spin one way and the other would spin the other. And I can't do it at the same time because it hurts I can't physically do it without hurting my head. I have to think too hard. And so these 2 different spins, we call them, like to abbreviate it, we have an m sub s is plus 1/2 or minus 1/2 to indicate if it's which direction the spin is. And we often refer to it as spin up if it's plus 1/2 and spin down if it's negative 1/2. And we'll see that within an orbital like an m sub L, so a shape within a specific orientation relative to the nucleus, each of those orbitals can contain 2 electrons, but one will be spin up and one will be spin down. And so they'll have opposite spins. We can't have 2 electrons with the same spin in the same space. And so this is going to bring us to 4 quantum numbers that'll describe where or how an electron is structured within an atom, like where its position is in that structure. And every electron within it will have a unique set of 4 quantum numbers. So it's like my house address is unique to my house, whereas the street that I'm on is the same as my neighbor's street, right? But they have a different house number. And so as you go from kind of broad, like I live in Washington, I live in Seattle, I live on this street, and then I live at this house number, our quantum numbers go from really broad to narrow too. We have our quantum principal number n, which is like, here's the general energy level. Then we have L, here's the shape of the orbital. We have m sub L, which is like, here's the orientation in space, and then m sub s, which is the spin up or spin down. And so the Pauli exclusion principle is that our electrons, 4 quantum numbers combined, has to be unique to that electron within the atom.